Welcome to Lyons Township High School AP Physics. Today we got an example involving a collision between a baseball and a box. So first thing you might want to do is copy down the diagram that we've got. So give that a shot. All right. So it's real simple. We'll call the baseball little m, about 142 grams, moving at some velocity v naught that we don't know. It's going to collide and stick to a 500 gram box. And then they're going to slide a distance of 20 meters. We're going to say the coefficient of kinetic friction between the box and the ground is 0.2, okay? And we're going to be using that number. And my question is really simple. How fast is the baseball going to make this occur? So now it takes a little bit of work to get there, no pun intended, but we'll figure it out. So we've got basically three spots of interest, okay? We have before the collision, okay, so we'll call that A. This is before the ball hit the box. We'll call that A. We've got immediately after the ball has collided with the box and the two objects are moving together at some velocity that we don't know. We'll call that point B. That's, again, the moment that they're stuck together and moving. And then they slide to a stop, and wherever they stop, we'll call that point C, and I've given you a distance of how far they slid, which is pretty far, by the way. So, question is, how fast was the ball going, okay? Well, we're going to study each part of the motion, A to B and then B to C. So starting with A to B. Going from A to B, what do we have? Well, we have a collision. And whenever you have a collision, the total momentum for the objects involved in the collision immediately before and immediately after the collision is the same, otherwise known as momentum is conserved. So the total momentum at point A is going to equal the total momentum at point B. Now, at point A, the baseball has momentum, it's moving, so that's little m times v naught. Okay, we'll throw numbers in a minute. The box is not moving, so I'll put the 0 there just to remind us that the box isn't moving before the collision. After the collision, they are moving together. So that would be little m plus big M. They are stuck together as one big mass times some velocity v, which I don't know either, okay? So we got two unknowns here. I don't know v naught and I don't know v. I do know all the masses. I'll throw those in. And by the way, because I've got this mv on this side and mv on that side, it doesn't matter what unit you use for mass because they'll cancel out anyway, so I'll leave it in grams. So we got 142 v naught equals 500 plus 142 is 642 v. Okay, so I've got one equation, but I've got two unknowns. So what else do I do? Well, going from B to C, well, now the box is sliding to a halt. Okay, so there's a couple ways you can analyze that. When two objects interact, they're usually thinking momentum. When an object moves from one point to another, you're usually thinking, or you should be thinking, energy. Use conservation of energy. So, from B to C, okay, we'll use conservation of energy. So the kinetic energy at point B plus the potential energy at point B plus any work done by any non-conservative forces between B and C is going to equal the kinetic energy at C plus the potential energy at C. Well, several of these things are 0. There's no springs in this problem and there's no change in height in this problem, so there's no potential energy before or after. And, well, when the box gets to point C, it's not moving anymore. It's slid to a stop, so this is 0. So our equation becomes pretty easy. You got kinetic energy at B plus work done by non-conservative forces has to equal 0, which, by the way, leads you to the realization, hopefully, that this term has to be negative, right? So what forces are acting on the box? What's doing this non-conservative work? Well, let's draw an FBD of the box as it's sliding. I'll draw the FBD right here. As it's sliding from B to C, well, you got weight, so this is big M plus little m g, right? The box and the ball, okay? You got the ground pushing up on the box, that's Fn. Because the box is not accelerating up or down, and because there's no other vertical forces involved in the problem, these two forces are going to be equal. And as the box slides to the right, now remember this is after the baseball's hit it, it's just sliding. Well, what's stopping it? Friction. And that friction force is going to point this way. It's going to point the opposite way of the motion and stop the box. So we're going to need to find that force of friction. So over here I'll do that. We've got force of friction equals mu sub k Fn. Okay? And in our problem we just discussed that Fn is equal to little m plus big mg. So force of friction equals mu sub k times big M plus little m times, or that's it. That's your force of friction. All right, now, what's the work done by that force? Well, work is force times distance. So, next line down, kinetic energy at B is 1/2 m, well, what's m? Well, it's the box and the ball moving together, so better put those both in there. Big M plus little m. V squared. Now what V is that? Well, that's the velocity at B. That was immediately after the collision. Well, that's this velocity right here. This and this are the same thing, okay? Work done by friction. Well, the motion's to the right, friction is acting left. Since the force is acting in the opposite direction of the motion, that force is doing negative work and sucking energy out of the box. So this is minus the force of friction times distance. That's the work done by friction as the box slides from B to C, and that equals 0. And so then we have 1/2 big M plus little m V squared. I'm going to move friction to the other side, make it positive, so we got equals, and that force of friction is equal to mu sub k times big M plus little m. So we've got mu sub k times big M plus little m times d. You'll notice the masses drop out. That's why, one of the reasons why I don't ever plug them in. I try not to plug stuff in until I absolutely have to. So these are gone, okay? And I'm not solving for V naught. I'm solving for this V. So that V, well, I'll write the V squared in there. So V squared, if I multiply by 2 on both sides, is 2 mu sub k times d. And so V would be root 2 times mu sub k times d. So that's the velocity of the box and ball immediately after they collided. And you could plug numbers in and get a number. I went ahead and did that. So, oh, and I almost forgot something. Oh my goodness. Some of you are going nuts right now because you see something that I forgot. Okay, did you guys catch it? Did you guys catch it? Fn, big M plus little m times g. Oh my goodness. All right, let's add that in here. That's there, right? And then that's there, right? Now, by the way, this is one reason why you show all your work. It's very easy to fix. And then that goes right there and right there. All right, that's an easy fix. Some of you guys were just absolutely going crazy, weren't you? Because you saw I messed that up. But caught my error. All right, so V equals the square root of 2. Mu is 0.2. D was 20, and G is 9.8. And I got a number. Oh, well, I'll get the root out of there. When I plugged those numbers into my calculator, I got like 8.85 meters per second, which is, I don't know, just under 20 miles an hour or so. All right, now, what's V naught? Okay, how fast was the ball going before the collision? So we're going to take that number, and that's V here too. So we're going to plug that number in right there, okay? Or we'll do it right here where we have numbers. So we've got 142 V naught equals 642 times our 8.85. And if you solve for V naught, I got right around 40 meters per second. That's the velocity of the baseball before it impacted the box. That's about almost 90 miles an hour, so that would be a major league pitch. So there you go. So again, big picture items. Split your problem up into pieces. You got A and you got B and you got C. Look at each part, going from A to B. Well, then you have two objects interacting. When two objects interact, you should think momentum. Then from B to C, it's one object moving. If you got one object moving from one point to another, you should usually think conservation of energy. Put the two together and you solve for what you needed to. So I hope that was helpful, and thank you very much.